So welcome to, this is now lecture number 8 in the summer term 2025. In parallel and distributed computing, today we are talking about C threads and OpenMP, and either when you are here or this, you are looking for this on YouTube, then because today we're encountering a lot of technical problems, something came up here, technical problems. I cannot log into the cluster, and actually I wanted to show a lot of stuff. So the lot of stuff, last year I recorded everything. Yeah, so last year's recording of this, of lecture 8, and also the exercises. I made 3 videos last year on this. That's maybe a better resource if you want to recapture this lecture. You go to last year's recording. So this is maybe the advantage of having these recordings when the technology breaks down. Now we are talking. We try first to do some theory, and when Konstantin is, maybe you sit down so that they can see over your. When Konstantin is able to recover something, we'll try to go into the practice thing later. But let us just get started with the theory. Okay, so we are leaving MPI a little bit away now, and we look at other possibilities to do parallel programming in C++. So we'll talk about threads, we'll talk a little bit about mutexes and atomics, and in the end we'll also go to MPI. So C++ threads, this is a possibility to allow you concurrent programming. Concurrent programming, in a sense, is kind of also a little bit different from or more inclusive, you may say, compared to what we usually do in MPI, where all of the nodes execute the same code. Yeah. So with threads are often used not to do the same thing multiple times, but you could do a completely different things. Like one thread is dealing with the user interface, and another is doing some computation, and yet another is looking for updates and so on, right? So these can be completely different things. So threads, you don't need to install anything. This is part of the C++ standards in C++ 11. What you would need to do is you would have to include the header for threads, and then you can use them. The way you're using them is you define a thread as standard. You start a thread, let's say, with standard. So this is a namespace standard thread, and you will start a thread by calling a function that is supposed to be executed by the thread. So this function has to be defined beforehand. And so this is the first argument here, and then you give a list of arguments. So and the list of arguments matches the arguments of the function that you want to execute. So from here on, you send off a thread that, this function here will return immediately. Yeah? So it has started the thread, and the main function will just continue on. And if you just start the thread and you would then go to the end of your program, everything would terminate and you've done nothing. So what you also have to do is at the end of your program, or at the end where the threads are supposed to have done their work, you have to join the thread with the main thread. So actually this is basically like a wait statement or barrier where we just wait for that particular thread to arrive here. And as long as the thread has not terminated, the calling function will not yet go on. So example together with race condition. So what we would have to do here, so unfortunately, maybe Konstantin will help us doing some code which will then not become recorded because it's on the other computer. Okay, we get IO stream and we get threads, and now this is a very simple example where we simply count something upward. Yeah? So we need to have a function. This function needs to be of type void. So if this is supposed to return something, then put it into, your argument. So this takes a counter, and then it will count from 1 to 100,000. Okay, so how is this thing called? We then have a main function. Yeah, where say we start with a counter 0, then we generate threads. So threads are dealt with as like variables. Yeah, so they are simply of type threads. So standard thread T1. Yeah, so now it's generated. And we call it with increments, and then we give as additional arguments to this constructor, we give the arguments for this function, which, it's expecting a reference, so we have to turn this counter into a reference such that it does not try to pass it by value. Yeah? But as a reference. So that it will actually count on counter. So we're doing this twice and we give counter twice. So now what they will do is they both are trying to increment the same counter. Yeah, that's the only thing that makes it interesting here, because otherwise it would just count from 0 to something. Yeah, it should be simple example. So afterwards we join them and then we give the result. So what will this do? And this is a clever way of doing stuff. Now the problem is that these threads, they run concurrently or in any arbitrary order. So it's not necessary to have a multi-core computer to run threads. So actually threads are much old. I mean, not C++ threads, but multi-threading is of course much multitasking. Yeah, so multitasking means there are several threads in running concurrently, and they also may run on the same machine, so they can either be one after the other, or they can be on different cores of your machine. So the operating system decides this for you, or the hardware somehow decides this for you, and you have very little control over this. So your control is just you start it and you join it. Yeah? So good style would be, this is not really necessary, to ask whether it's joinable, and then you join it. Okay. Now, problem being that this generates something that we call a race condition. A race condition is a condition where the behavior of your program depends on which of the concurrent threads are accessing a variable at which time and who is coming first. Yeah? So here you actually have, so I mean, you could say both of them add stuff up, so at the end you would assume that you get twice the amount that you added, right? But that's not necessarily the case, because if you think about this could be implemented in machine code, so it could happen like this, but it could also happen in a different way, because what your machine would do, if this is thread 1 or thread 2, is that the core that does the calculation in thread 1 would load this counter into a register and then would add 1 to this register and would write back this register. Yeah? Problem being, during that time, there's also T2 has loaded something into its register and adds 1 and then writes it back. So this thing here, this R2, if this happens like this, so T2 has read the counter before, and then it stores it, while T1 loads it after, before R2 has stored it, does some calculations and stores it later. So this means this here will be lost, yeah? Because this, depending on what your compiler does, can be counted as two operations. There are a load statement and an add statement. Okay, very simple example. Usually the examples are much more complicated and much more difficult to understand what is going wrong. Okay, so in order to avoid this, what you can use is mutual exclusion devices that we call mutexes. Yeah, mutex is, I think, no. Mutex just means mutual exclusion. So mutex is a little bit an old-fashioned way of dealing with things. We'll come in a minute to a little bit more modern way of doing stuff. So if you have a common resource where you want to be sure that only one thread at a time accesses this, you can use a mutex as a kind of a lock. So here we have a global variable. Maybe again this is not the absolute best style, but it's just a small example that should fit on one page. Yeah? Put a global variable for one mutex, and this mutex is locked in this increment function, and where before we encounter the counter, so everything that we do with the counter is in between the lock and the unlock. So what does this mean? there's one mutex. When the mutex is locked and another function comes and tries to lock the mutex again, this function is blocked until the function that holds the mutex unlocks this. Yeah? So you can see this here on this side. Say T1 comes first, it locks the mutex. So this means there is a stop sign. Sorry, this here is a little bit further up. Yeah, T2, you never know who is coming first. Yeah, T2, even if it started later, but for some crazy reason it arrives at the locked mutex first. So the mutex is locked, and then T1 comes and tries to lock the mutex too, but this way it can't because the mutex is already locked. So there's this big stop sign. So T2 can do whatever it likes to the counter, and once it's done, it unlocks the mutex, and only from here on does the now the first one get the lock. Actually, I should put when it recycles, yeah, it would try to lock the mutex again in the next cycle, but now it is T1 that holds the mutex. So here's nothing going on, and we have exclusive access. So mutexes are kind of a little bit old-fashioned style because they are not necessarily extremely efficient. Let me see. Nowadays we'll try to do it differently by using atomic operations. So atomic operations are operations, so atoms supposedly cannot be split apart. Yeah? So this means there's an operation that is simply cannot be disturbed by another operation. So if we define this counter to be an atomic, and we do this adding here, at least I hope this is. I'm not completely. I'm teaching here something that I myself are not using in my life very often. So I'm hoping that everything here has the correct nomenclature. But from a theoretical point of view, yeah, we love theoretical lectures. If the cluster doesn't work, yeah, the atomic operations are operations that cannot be split apart. So if you start this, if you start this operation, it will finish even if somebody else, if some other thread is trying to access the same variable at the same time. So this is a little bit more modern, and the reason here is that in order for this to work, we need the appropriate hardware. So an atomic operation is a hardware operation. Yeah? So the hardware has to support atomic operations. And old people like me remember the time when this was not the case. This is why we still have mutexes around. So they come from the past, if you will. Nowadays we have atomic operations, and we don't need to think about that anymore. However, your computer, your processor needs to have atomic operations. So they are supposedly usually more efficient than mutexes. I'm not sure whether they are also more or less efficient to the usual operations, I would guess that they may be less efficient than the usual operations because you have to specify them as being atomic. So I think there is some overhead that you would have. But again, this obviously depends on your hardware. Yeah? So there may be hardware where there's overhead, and there may be hardware there is no overhead. Okay. Now, Konstantin, have you succeeded with anything? Okay, I was, because now this is so for everybody online, you would have to look into old last year's lecture, because I was actually right. So now this is very stupid here. We wanted to look. In my office. Wait, wait. I have to. That could be possible. Wait, I don't know whether there's anything secret just on the screen. Okay, so because this is nobody's business. Yes, okay, Konstantin has, of course, a good idea. Hmm? This?
Yeah, new desktop. And you have
Okay.
new desktop, and then you can again
Yeah.
Okay, sorry.
Yeah. Okay, so I have to cut this out in the recording. I mean, maybe we'll there is. I hope this is actually now visible. Okay, so I wanted to do something completely. Can I make this larger? I think it's Control plus or something. Yeah. Okay, so we encountered a lot of problems. Konstantin, of course, has the right idea. I'm usually not using this from this computer, but since I was trying something out yesterday, it's already running. Let me see. Okay. We were, yes, so we are in this PVR 2025, and in this, what is this? No, we have to actually open it. So here we have my folder, and in my folder we have this, okay, I copied this Laplace 2D here, which I hope you also have picked up by now, as long as you may. Okay, we'll talk about the access to this later. So your homework is in this Laplace folder, and what you were supposed to do here is to implement these MPI versions here, so which now are empty, yeah. I remind you, this is the the serial code is for you to get started, and I remind you, this is the example where you're supposed to solve the heat equation. So solving the heat equation is already here in a serial version, yeah. So we have this mapper, which is now going to be important because we are going to talk about this a little bit. And we initialize our grid, and then we do our initialization of the entire grid. Then we start a timer, and this is actually the equation where we do our work here. Yeah. So this is the serial code, and other than these different MPI things that you are supposed to implement, we have here different implementation of these things. For example, we have it in CUDA. So we are unfortunately on this cluster, we are not able to run it in CUDA. This is why CUDA we'll cover some CUDA in a later lecture here, but it's only in theory. If you are very interested in doing some CUDA work, then you can have, for example, you can come to us and have a Studien project. Yeah, but this is because we do a lot of CUDA computation, but in this class we are only theoretical introduce CUDA. So what I was actually wanting to address is that other than this, we also have here a version that is covered by threads. Yeah. So, and now this is doing the same thing as the other code. It just includes threads here. And what we need for making it runnable with threads, somehow I've closed the serial version, I believe. Why don't I have, no, okay. It's just in the same, okay. So in the serial version, you see, in the serial version we start with the main function, right? And then inside the main function, we have this loop that is doing the calculation. In the threads we need to put the actual calculation into a function, because this function needs to be called by the different threads. So all of this function, which is simply taking the average between the four neighbors, is put into this function here that we calculate time step. So it takes the old data, it takes the new data, and then it takes the mapper, which we are going to talk a little bit about. Then it uses inner grid, entire grid, num threads, and yeah, okay, it also takes a thread ID. We need a thread ID. It's similar to what we do in MPI, because the thread needs to know what data it is supposed to deal with. So there are two ways we could potentially do this. We could either, okay, no. In principle, in order for the threads to know who the thread is, we have to hand it different data, different arguments. Now, problem being, and because this is solving a partial differential equation, we have a field data, and all of the threads need the same field data. So we cannot just cut out a piece and send this to one thread and you work on this. So we have to, in addition, we have to give an indication. We have to give an indication to what your name is, and this is here the thread ID. So from the thread ID, it is using the thread ID to find out which part of the domain it is supposed to compute. Yeah. So because there is an index over all nodes, yeah, I, that in this case here starts with thread ID, and see whether this is smaller than the inner crit size, and then it is increasing I plus num threads. Okay, and we come to this other version here in a minute. So, and then the thread is processing its part of the problem, yeah, and then when done it will return. So now what the main function does is it has to call out these threads. So what we've done here is we have size t num threads. The unsigned long size t. Okay, I've not written this program, I always have to say. I don't know why he's just said integer size t. So here's a type def. So he makes a type def unsigned long is size t. Good. The number of threads. The number of threads is just a number that we initialize with 1 for the in case that we don't get any other thing. So you know that the main function is called with the command line arguments, and we can actually get the command line. So if we have command line arguments, then we take the number of threads that we want to have out of the command line argument. So when we start it, we can set this on the command line. Okay. So other things, timer, are the same as previously. So then we use the number of threads to split up our inner domain, and this is done by, okay, we initialize the data fields, and somewhere here, right? Somewhere we need to now allocate our threads. So in our example that we had with our 2 threads, we could do this statically. We could say there's thread 1 and there's thread 2. Now, the number of threads, because we get them from the command line, are not known at compile time. Yeah? Because they are not known at compile time, we have to allocate them dynamically. And because threads are the same thing as variables, what we can do, we could either put them into an array, which again would mean we would need to know, and either we would call this with new, or we would have to know it at compile time. If we don't know the number of threads at compile time, the most elegant solution is maybe to use a vector of threads. So you'll use a standard vector of threads, and then you can fill this on with the size of number threads. Yeah, so this can be done at compile time, because this takes care about the allocation of the vector. Okay, so then in place of having, let me go back to the serial version, in place where we do this loop, here, yeah, we also do the loop, but what we do is we start here our threads. So we go from size t, again is an integer, an unsigned integer, for whatever reason they use this here. So that starts from 0 and goes to the number of threads, and then it generates these threads by calling threads I, yeah, standard threads, calculates the time steps, and then we hand over the references to this data. So we don't, by the way, let me see. Obviously, we don't want to pass the data by standard vector double, yes. Okay, so we don't want to pass the data by value, obviously. Yeah, that wouldn't make sense, because then it would do the, first of all, we would copy a lot of data, and the other thing is we would, we did the calculation and then everything was lost in the end of the function, right? So we'll pass this by reference. So we'll turn this into a reference. So then we call this everything with our, the number of threads and this I. Now this is the important thing, because this is your thread ID. Yeah? So this is the number of the thread. By this, the thread knows what part of the work it is supposed to do. So after doing all of this, we have to rejoin all the threads, and this is by having a loop over the threads. I always notice that this is for somebody as old as myself. This looks a little bit Python style, yeah, usually in C. So auto means it automatically determines what thread, what is the type of the thread, and then it just goes over the variable threads is what is inside threads, and then it joins the particular thread. I actually think that you should not overuse auto, because the good thing with C++ is there's a typed language, and this actually gives you gives you a safety layer. Yeah. But anyway, modern work like this. Yeah, and then the rest is the same as usual. So let me see whether I can find this. So you are supposed to copy these things anyway to your folder. We are all together in PVR 2025. Here my folder is obviously Gaia, and in this I have the Laplace, and now I don't know any further. We are potentially CD. Are we in bin or are we in build? No, we are in build. CD build. In build, there's also CMake text. Yes. Okay. So, did we go through the compilation of everything? So it may be there is the bin folder in which everything is generated. So maybe you have to when you copy everything and you call make, then maybe this wouldn't work for your case, because you have a different path. So you'll go through the CMake. Konstantin, am I making this correctly? I have to, or do I have to go to the into the bin in order? No, I make point, but then it's then the make then the CMake list is in the previous folder. No, really? Okay, apparently. Okay, so what CMake actually does, it's generating a make function and this make function, but the make function. Okay, I go to bin now. I want. Okay, do I call make here and then it produces the build itself there from here on? Yes. Okay, good. So, okay, so because I've done this already, so it compiles everything, or it tries to compile everything, but it was already compiled. This is why it was so quickly. Yeah. So now we are, at least we made clear that we are in this particular in the same state that we had here, and then we can go to cd bin where we have all of these examples. So I'm going to do something again which you are not supposed to do, namely to run on the login nodes just for demonstration. Yeah, we have this. Let me see. Let us just run the Laplace serial stuff. So this is, you see, this timing here is what we call million node updates per second. So this is how quickly it runs in the serial version. I'm not going to. This is just for demonstration style now. Yeah. So you see they are kind of 300-ish. Yeah. So when I run the multi-thread version and I run this without arguments, then you saw in the code that it will run with one thread. And okay, so what you discover is that using threads comes at a cost. Yeah? Because the other one was running with one thread too. Actually, okay, good question. With how many threads does this program run? When you generate one thread, how many threads are running? This is a trick question, apparently. Don't be so shy. Well, it will be two, because you have the main thread and this calls another thread. So there are two threads running, right? Okay. So this comes at a cost. So the thing that we wanted to try, now if we take, for example, 4. So obviously this runs faster. So it does not really run 4 times as fast, right? Yeah, so there's more overhead. So let me see, run it 10. Oh. It's a little bit disappointing, yeah? It's a bit disappointing. So I guess 20 would be the most, because this machine has 20 threads. Okay, let it be for this for a minute, and coming to something that now, because I had I was trying to prepare this a little bit better than I had the opportunity to. So now I'm making a mess in my explanation here. But let us at least think this through. Maybe we come to a better point now online. When you do parallel computation, there are several things that you have to take into your consideration. And one of this is, suppose you are splitting up your domain, then there is different ways how you could split up your domain, and this must be in sync with both how your programming language works, how your setup works, and how your processor works. Yeah. So there's a lot of thinking. There should be a lot of thinking involved, and not everything behaves exactly the way you may be expecting this. So I remind you about the use of this class mapper2d, which is, I believe, not defined. See, this is defined in this one here, and it's used by all of them. So mapper2d is you got okay. So you get the position. So this is what you would often use. So if x and y, yeah, you have a position x and y, and this is mapped to a one-dimensional array, because all memory in essence is one-dimensional, and we want to have this under control. And what you see is that x is the fast variable, and y, or no, x is the okay, I should not say fast. X is the consecutive variable, and y is the one that is non-consecutive. Yeah. So then I told you that when you go over a loop, the innermost loop should loop over x such that you always deal with continuous variables. Yeah? Now the question is, how do we do this with these threads? So okay, this is basically what is written here, and now we want to know how to deal with how to combine this with our computer, and our computer will always be different, the one that we have here. And if you know something about processors, you'll say, what on earth is this? So this computer is supposed to be demolished at the end of the year, and it has been so for the last 5 years or so. So we are kind of on an old machine. Yeah. So each of our compute nodes has 2 Xeon processors of this kind. Each of them has 10 cores. I mean, it looks big, but it's also an expensive machine. Yeah, it was an expensive machine 11 years ago. Yeah. This has 3 different levels of cache, and then it also has different amounts, a specific way of addressing its memory. So this machine has, for each processor, 2 memory banks with 8 gigabytes each, which means that if you have to address if a thread that lives in this memory here, if a thread that lives in this memory here, it can directly address this memory when it's on this core, yeah, it has its private L1 and L2 cache. All these guys here together have a common L3 cache, and they access together these two memory from these two memory banks. So they may also sometimes access memory on the that is attached to the other processor, yeah, because we have a common memory space. And when we do this, we go actually not directly to the other memory, but we go from this processor to the other processor by something that's called quick path interconnect, yeah, which is of course a marketing name, and it may also be fast, so it has 9.6 giga transfers per second, yeah, but you know, this still has to go through the bus here, so I mean, whenever you need to use two buses, it will be slower than just using one bus, even if the first bus is a very fast bus, yeah, so accessing memory further away will be more expensive than accessing local memory. So, and whether this is, I mean, this is not necessarily easy for you to know whether this happens or not, but this will change the performance of your code. So this is the machine that we have to deal with. And now comes the question, what is the optimal way of dividing our threads? And this can actually be a little bit counterintuitive. And for this reason, I'm not trying to be too much explanatory. We'll do that what Konstantin actually likes very much, is called empirical programming. Yeah, so empirical programming, even though your professor may tell you you should always think rather than do, and in practice you do and see, yeah, you do some experiments. So this is what people do and how the world works, yeah. So let's just do. What we did here is we increased inside our threads, when we were processing our nodes, we increased by the number, we increased the index by the number of threads. So we were actually going in the y direction, yeah. So two nodes that we are processing are not, they are not next to each other. Yeah, so we always go by this entire step. So we can also do it the other way around and go in x direction. So maybe this is not completely on the screen now. So we start from thread ID inner grid divided by the a little bit more complicated, but you know, the thing is you'll just increase I by 1 each time. So you're going in the direction that is connected to each other. Yeah. So I've gone through. Let me see. I think I have to go here again. And no, very, very important. I always forget this. We have to save this. Yeah, because my other IDE does this automatically. So I'm going to forget this. So we changed it. We call make again. So all the others are, you know, all already done. This is why it only replaces these ones. Then we go to CD bin, and what we are going to do is we're running this again with, say, 10. Which is of the order, we want to run it through. I guess it takes roughly a minute or something. Okay, so there's a back down there is a limit. I think yes. So okay, we got 586 for this version, and then I go mine's threads here. Okay, then I go again here. So you keep this in mind. 586. I save this. So again, we'll now going in Y direction. CD make. We'll compile CD bin and run. Okay, I think we'll already see that this one here is slower. Do we agree that this is slower? Was 500 something? You know, the problem when it's slower, we have to wait longer. I mean, it's convincingly slower. Okay, so 580 something, 340 makes a difference, right? Okay, so the yeah, so the okay, so so the number. Okay, so what does it mean? We should look at the time. Yes. So the time was 43, and the time is 75. Okay, so right. So the one that is slow is actually what we may have expected, that if we count, you know, when x is the continuous version and then we count over y, this is the discontinuous. So now this leaves me completely in trouble, because you see this is a bad thing if your computer doesn't work and you cannot prepare it precisely. And I still have to admit that I'm giving a lecture that I've not myself developed. So somebody else put here the green light to this and said this is a good access pattern, and that is the bad access pattern. Now empirically, it was the other way around. Now should we be concerned? What should this tell us? Okay, let's say this tells us that you should not believe me or should not believe theory, but that you should always try it out. I think this is the best message that we get out of this. So how comes we have this prepared this way? I mean, okay, you can go back to last year's lecture and see how whether last year it worked the other way around. Maybe it was because of 10 threads, and with another number it would be different. Yeah, so it may, it may depend on a lot of details. Okay, take as a message, try it out, okay? Because it may be very counterintuitive. Okay, so let's come to the next version that we have is OpenMP. OpenMP is yet a different philosophy from both threads and MPI, even though it sounds a lot like MPI, yeah, but it has a completely different meaning. MPI is not directly part of a standard, so we have to compile this with this particular option, OpenMP. And compared to MPI, it is not for distributed memory system, but is particular for shared memory systems, and therefore it also behaves a lot differently. However, it is usually much simpler. So if you can use OpenMP, so parallelization by OpenMP is usually the easiest thing that you can do, because what you often do with OpenMP, even though OpenMP can do lots of other things too, but the simplest way of applying OpenMP is to tell OpenMP that you have here a loop, and then you want this loop to be executed in parallel. Yeah? So, of course, this means that your loop is written in such a way that you can run it in parallel. Yeah? So if your loop is iterating over the same value, then of course it cannot run in parallel. Yeah? That must be, this is of course necessary. So basically all you need to do is to tell OpenMP that there is this loop that you want to parallelize. Then the way it is parallelized, so how many threads are used in the parallelization is taken care of by the operating system according to an environment variable called OMP num threads, for example, 4. Yeah. So this variable has to be set, or in the Slurm, is it called the Slurm file? In the batch file. Yeah, in the batch file, this parameter has to be set in order to for the machine to know how many threads you are going to use here. Okay, example. So guess the example actually comes directly from our code. Let me briefly go back to this code. You see, we have here an OpenMP thing. For this OpenMP, we don't need to load a header, at least not in this case, because we are using only the simple functionality. But when we compile it, we have to use the compiler flag, which the make file takes care for us already, right? So, actually this thing here looks very much like the original serial version. Maybe, let me see, maybe up to, right. So, you see, we come to line 60. in the serial version, yeah, up to here nothing changed. Then we come to OpenMP, we get this one additional line. Oh, see, it's so simple, yeah? One additional line, pragma. So this is a pre-compiler directive, pragma, yeah? OpenMP parallel for default shared, private x, y. So let me briefly go here back to this is the same that we've taken out, and here a few explanations. Namely, so this default shared is telling the compiler what it is supposed to do with the inner variables here. So variables that are outside of that scope, the scope of that for. The scope of the for is indicated by these two brackets, the scope of the for. So all variables outside this are shared variables. Yeah? And it's important to understand the difference between OpenMP and MPI, because in MPI, the distributed memory, all of the threads or processes have different variables. Yeah? Here, OpenMP, all of them have the same variables outside that scope. Now, this default shared is telling the compiler that by default, also inside the scope, all the variables have the same value. Are shared variables, shared between the threads. There is one exception that you don't need to tell the compiler, and this exception is the iterator. The iterator is never shared, because this is how the loop knows where the loop is split according to the iterator. Yeah, so the iterator is always local. Now, otherwise, you would have a problem within this if you define if you use some variables like x and y, and you use them shared, because in this loop here, you first compute x and y from the position, and if another thread is doing this in parallel, they would overwrite your x and y. Therefore, you need to make sure that x and y, even though everything else would be by default local, shared, yeah, but x and y are private. So private is not private in the sense of private variables in a class. Yeah? They are private to your process or thread in the MPI. So this in the OpenMP. This means that while another thread that is doing the same loop is overwriting x and y, they have their own x and y. Yeah? So we put them to private. This is private to my thread. So private here you give the list of variables, and I, as I already said, is by default is its own. So this is now all we need to know here. And now we also have to be able to run this in the correct way. So we are already in bin. What we now can do is we can run this. What is this? Wait, what is the name? This, yeah, Laplace. So, by the way, here nothing changed. The main doesn't take any arguments here. Laplace OpenMP. Okay, so it's a bit faster. This may, okay, so there is one thing, because I had this particular thing open, this terminal open from yesterday, so it may be that I've prepared something that I wanted to do actually only later. Namely, we have to look into this variable in this environment variable OpenMP num threads. Because, I mean, this is nothing that is by default, this is not set. Yeah, let us see whether it's now set. No, it's not set. Okay, was still fast enough. You see, this is the problem when you are not well prepared for a lecture, that I have an excuse. So maybe if it's not set, because it is possible if it's not set, it uses as many threads as possible. It should not. Okay, let me see. I set this to 1. Okay. So that would mean that this here runs with 1 thread. And you see it's considerably slower actually than the serial version. That also runs with 1 thread, yeah? Because there we have the overhead, but we don't have any use. So I'm a bit surprised that if you don't set it, then apparently it automatically takes what it has, maybe, yeah? That's when I put it to 10. Okay, so it's 800-ish. It looked a little bit larger, so we have 20. Let me see whether yeah, so maybe your computer knows better than you how many threads you should use. Maybe didn't actually improve that. No, what, sorry, that was the, I wanted to, let's do it with 4. Okay, I guess that 4 has, you see, 4 is pretty much 4 times as fast as 1, but it is considerably, but it's roughly the same speed as the serial as the serial version. Yeah. So we've eliminated the overhead. Okay. Yes, that's. Okay, let this be. Okay, I have 2 more old things. I told you to install PowerView. Have you already succeeded in this one? If not, then there is a reminder that you have to go to PowerView.org, yeah, and the thing then being, so the cluster is not able, actually it is able, but this is not what we are teaching here, and you're not supposed to use the visualization nodes on the cluster because there are only very few, yeah, and we are guests on this cluster. So what you are supposed to do once you have your result, once you got your result, and your result will be written in this temp outputs.imp. So you are supposed to download this thing and open this on your own computer. Yeah? And for this, you need to have this power view, and you just go there and download it. And you are basically done. So, other than this, before we come to a little bit of exercise, I had one thing that I would actually wanted to tell you in the beginning. Oh no, this is still not, this is the right way. So I wanted to start the lecture today with telling you what mess I did last time. So maybe if somebody is watching the videos, I'm in the habit that even if I'm making a complete fool of myself, I usually leave the things up there so that people have something to enjoy, yeah, even though they're enjoying me being stupid. So let's come back to our problem that we could not solve last time, and I wanted to tell you what the problem was. Yeah. So this is also what we are going to continue now in the exercise session. You remember in lecture 7 or exercise 7, we had this. We computed this function pi, and we did this here by divide and conquer. And if I go back to this CD, let me see, CD, where am I? CD lecture 7. So, let me see. So, right. So we implemented this divide and conquer thing, where, just as a reminder, so everybody is sending stuff to their, or the slaves are sending stuff to their master, yeah, and then they disappear, and then the master collects the data and sends to their master. Yeah, so this is what we mean by divide and conquer. Whereas when we just have master slave, all the slaves send to the same master. Yeah, but here now we have a tree that is converging, and this means that there's also by pure master slave there's only one master that collects everything, and here the slaves are slaves to particular master that then later becomes a slave again. So everybody, okay, so this, so the receiver, so, okay, you receive stuff and everybody is sending stuff unless they have rang 0, because rang 0 is the master, yeah, that is only receiving stuff and it's not sending it out again. Now we implemented this and this didn't work, so CD, no, we are already here, MPI C++ main thug minus O P DC. So let's compile it and then run it. MPI run minus. Okay, so since it's a tree, it's better to run it with 8, 4, 8, 16, or 32 or something. Pi these P not be like this. So once we run this, we run into trouble, and the trouble we ran into was that we get first floating point exception and then integer division by 0. Okay, and during the lecture I was kind of not able to determine what was going on. Okay, of course I've seen this here, which is very bad style, but I thought that style didn't really matter. What I've done here is I put the question whether my rank is not 0 inside the loop. Yeah. So this is of course stupid. You should never do something like this, because I mean my rank will always be either not 0 or so for all these cases. So if you put it outside, it will ask it only once. If you put it inside the loop, it will ask it again and again. But for whatever reason, I did this in here, and other that this is inefficient, I did not see that we have a problem here. Because what I was thinking is, we are just increasing offset all the time. I take my rank, which can be either 0 or something else, and then I do a modulo operation of this and check whether this is equal to 0. So there is nothing bad happening here. Yeah. So because this offset is obviously an increasing function, so it's always larger than 0. Then I divide by something that's larger than 0. So why should I get a division by 0 thing? But I get a division by 0, and this is actually happening here. So what is the problem here? Oh. By the way, okay, I said something else stupid. This is not, okay, my rank is not inside this, yeah, so the loop was only to get to the right offset. Yeah, so this is not actually asked inside here. Yeah, okay, so this was a mistake that I just made. However, the loop is run before we check whether we are 0. Now the problem is the following. If my rank is 0, this here is 0, so this will never, so this is always 0. Yeah? So this will never terminate. So if this is never terminating, this is just counting, so multiplying offset by 2 all the time. Which, when you start from 1, is just shifting, so it's going from in binary 0001 to 0010 and so on, yeah, until it arrives at the end, and then if you multiply it by 2, it becomes 0, because you have an overflow. You're running this because there is no other stopping condition. You're running this into overflow, and then when you've just been in overflow, it becomes 0, and then you have a division by 0. So this is the stupid thing here. And therefore, what you need to do, very simply, is to put this to the outside. Yeah? So these are typical, difficult to find error, because I was not thinking about the overflow. So if you save this and compile this again and run it again, you get the right result. Okay? So maybe it's all on the recording, so if somebody watches the recording, they may see, oh, it's completely clear. By the way, I gave this to ChatGPT, it also didn't find it. So, okay, right. So we are in time of a break, and what we are going to do then is to take this, basically this code here, and try to implement it with threads and with OpenMP. Yeah, so this is what we are trying to do for the exercise today, and I'm going to stop the recording now.